the day we got like so like flat.
Yeah, you like open it and it's
Everything else.
yeah.
Life is
Yeah, I'm sure I
Have the belt that someone got right.
the only like even like for
Yeah.
so it's giving me like
I got it. Yeah, I would never buy it.
come back to life. But like I enjoy it.
already said it.
I enjoy it. I enjoy I've been here and don't like it was one of those things where it's like
Yeah, yeah, it was on the last one.
Good morning. All right. It's a bittersweet morning. Next semester, there you go. All right, so last class. We'll round out talking about special relativity. As you know, this is a brief introduction. I've been thinking a bit this week, particularly since Tuesday, of how far I want to go with this. And in particular of interest to you, how far I want to go with this in terms of anything that might appear on a test. And so what I've decided, I'm slightly behind where I expected or hoped to be by today, by maybe half a lecture or so. And so what I definitely don't like to do is kind of have things be very rushed and hasty right at the end. It's not a good feeling. So I think what I want to do is pretty much in terms of material on special relativity that, let me say, I want you to know for the final. It's going to go up to and include what I believe is section 37.5 in your textbook. And it's not a lot of stuff. It basically takes us through simultaneity, time dilation, length contraction, which we're about to talk about, and the Lorentz transformations. And it pretty much gets that far. So what I am going to talk about today in class, but I'm not going to kind of expect you to know for any test, is we're not going to have stuff on relativistic momentum and relativistic energy be anything that you'll be tested on. But I will talk about it today because I kind of feel it's interesting. And so I think that's where I want to define the sort of cutoff point. And so what are the implications of that? I'll probably put up something like 5 or 6-ish additional problems on those aspects of special relativity, those things that I mentioned up to and including, I think, section 37.5. I'm going to put up a few problems on this in Master in Physics as a non-graded problem set, okay? So obviously non-graded. However, I do want you to do them, okay? We've only had, I think, 3 or 4 graded problems on this week's homework on special relativity, and that's not quite enough to exercise you. So I'm going to put these up as soon as I can, likely tomorrow at this point. And again, please do them, it's going to be good for you. I'm going to choose them as best I can to be sort of gentle in introducing you to the sort of small number of variant type problems that you might do on those topics. And I'm going to try and make them be kind of really learning problems, a little bit in the mode of the practice problem set. So that's where I want to kind of 10 things. Again, I'll talk more about other aspects of special relativity later in the class this morning, but it's kind of on an FYI basis and maybe just interesting, but nothing that will be tested on. So formally, recitations will have wrapped up by now, but as I think I mentioned on Tuesday, Ben and Reese are available, certainly next week and possibly the week after. I have to talk with them about exactly what that means, but I want some input from you on this. It's probably, I think, not worth their while to have a full suite of 6 recitations next week, and certainly not the week after. But again, they're willing to be available, and that's great, so I'd like to take advantage of that. You don't have classes after Monday, so in principle you're semi-available. So I guess what I'm kind of curious to get some sense of input from you on is if we were to set a more limited set of offerings for recitations next week and probably some level the week after, what times are going to work best for you? So I think I'm going to try and make these at least overlap with some of the original recitation times, just so it's not super confusing. So let me just try and poll you and get a sense of what might work. So let's see, we have Tuesday and Wednesday, and the standard times we have, I guess. Tell me if I'm wrong on this, I haven't looked at it in a while. Those are the standard recitation times. Let me just quickly get a show of hands in terms of when, if you're interested in coming to these, and I hope all of you will. Not only next week will they have a chance for you to talk about some problems in special relativity, but there'll be an opportunity to just talk about anything in the course. And again, we have this not next week, but also the week after, somewhat in the sense of just review questions. So I just want to get a sense from you what the most popular times are on this, okay? So if you can make any of the times as I quickly go through them, just raise your hand. I know this is a bit hard to pin down, but I want to do the best guess. So Tuesday, 4 to 5. So half-ish of the class. Tuesday, 5 to 6. Possibly slightly more. Interesting. Tuesday, 6 to 7. I'm going to go back to a half. Wednesday, 4 to 5. Oh, popular hour. Maybe 2/3. Maybe. Yeah. Wednesday, 5 to 6. Plus. Wednesday, 6 to 7. About the same. All right. Well, that's not giving me much to go on, but okay. All right. So I'm going to talk to Ben and Reese and see what their availability is like. Okay. Yes, don't know what I'm going to do with this. I'm not going to try and attempt this as an exercise in terms of office hours for me. I'm around for the next couple of weeks. I think what I will do is just look at my schedule, find some time slots that I'm available, and just sort of randomly circulate some hours that I'll be available next week and the week after, okay, for consultation on anything to do with the course. And a reminder, which I didn't put up on here, that there are the 2 review sessions next Wednesday afternoon and Thursday morning, okay? So those are on your calendars in CourseWorks. Please try and fold one of those into your scheduling next week. You can come to both, of course, if you wish. It'll be basically the same stuff. Okay. And then hopefully by the weekend, I've got a busy couple of days, so I'm not up here until later in the weekend. This will be relatively fast, a clear summary of material that I want you to know for the final. In terms of the chapters we've covered, 1 through 13 plus 37, there isn't much that we're skipping, but I'll try and make it clear where there are things that I'm not worried about you knowing. And then more usefully perhaps for you, and I've been suggesting this to a few of you in conversations in the past few days, at this point as you're kind of preparing with a look back over the semester, what I find is often the case, now that you have a little bit more of a sense of the big picture, is going back and looking at those problem-solving strategy menus, I think is perhaps more useful at this point, and it's more essential at this point because you've built up to some extent a kind of set of tools that may or may not be applicable for solving certain types of problems. And I think now that you can look back and sort of more absorb what the criteria are for being able to apply certain strategies, it's good to kind of compile those strategies together and again make sure when you're figuring out which ones you want to use or thinking of using that the criteria that are necessary to use them, you've understood them and you've thought through them carefully. So what I've been suggesting to a few of you is to write those problem-solving strategy lists yourself, but take extra or pay extra attention to now going back and saying, okay, I can only apply, for example, energy conservation if no net external work is being done on my system, or if it is, I have to explicitly fold that into my energy balance accounting. So what I'm kind of suggesting would be helpful to all of you, and I'm going to kind of do it myself and then post this on Courseworks, is to set up that sort of list of problem-solving strategies with the attention paid to the preconditions or prerequisites, if you will. So I'm going to do that. I wouldn't, if I were you, rely on what I post. It's much more beneficial to you if you do it yourself. Think through it, and again, put in those prerequisites, so to speak, to applications of those strategies. You'll find that much more powerful than just looking at what I post, but I'm going to post them anyway. Okay? All right. Lastly, and then I'm quickly going to ask for inputs on questions on anything, and then we'll talk about special relativity for the hour. For those of you who had submitted midterm 2 regrades, beyond the ones that I returned on Tuesday, they're here, so feel free to pick those up at the end of the class. All right, questions on anything? Good? Okay. So, let's see if I can pull this back up. Okay, this is not a good sign. Okay. Live. Okay, good. All right, so I'm going to do this slide-based as I did on Tuesday because I think it's kind of, in some ways, a more helpful way to learn some things about special relativity. You'll have seen I've posted a couple of suggestions for additional resources for special relativity. Some inputs there. This was the summary slide from the start of Tuesday's class. And as mentioned, in terms of what I might worry about testing you on, we're pretty much going to stop at this point with Lorentz transformations. But I will talk about this stuff down here today just because I think it's very interesting and I'd like you to be aware of those aspects. So let me quickly jump down to where we left off. Tuesday. Okay. so what we talked about in Tuesday's class was initially looking at this idea of whether things are simultaneous, and by looking at sort of a pair of events, let's say light flashes are the standard sort of things we might look at. What we learned right off the bat is the idea that whether we claim two events are simultaneous or not very much depends on our reference frame and whether we're moving one reference frame with respect to another. And then we pretty much followed on into a thought experiment that would basically motivate this somewhat surprising phenomenon of so-called time dilation. And what we learned from that by looking at light travel in two reference frames, one from the perspective of an observer that we're going to count as stationary compared to a second observer that's moving, is in fact that the time measured on clocks in those two reference frames differs. And so the sort of punchline of this is that if you are observing a clock move, or a clock in a moving reference frame, that clock will appear to have time run slower. So time ticks more slowly when you observe a clock in a moving reference frame, and this is the phenomenon of time dilation. Okay? And that sort of simple thought experiment, which has very simple geometry, basically just Pythagoras theorem, allows us to derive an expression for the factor that relates those two time intervals that are measured, the so-called Lorentz or gamma factor. And of course that gamma factor is going to appear in other places as we look at more general transformations, and in particular when we look at this related phenomenon of length contraction. So the gamma factor, let me just remind you of this, it came up in office hours quite a bit. Maybe I'll write this down. So there it is, and of course this is our speed of motion of the object, and just to remind you first off that gamma is greater than or equal to 1, depending on what v is, and also to remind you that in order for this to deviate appreciably from 1, v has to be a pretty substantial fraction of the speed of light, okay? So this effect occurs for all speeds, but it's only a really significant modification when this gets to a large fraction of the speed of light. Okay, so there's our gamma factor. So that's kind of where we wrapped up on Tuesday. So let me come back and talk a bit more generally about the idea of transformations between different frames of reference. And this is going to lead us towards the Lorentz transformations that are what we need to work with in special relativity. So, okay, so what's a transformation? It's basically just some operation, and that for us, in our case, is going to allow us to transform between two different reference frames, two different coordinate systems, if you will. And it's going to turn out, in special relativity, the ones that are relevant, and these are, as always, remember, between inertial reference frames. So things that are moving at constant velocity. We're not going to complicate our lives by any acceleration. That immediately ties us into general relativity, so it's a little bit beyond the scope of anything we want to think about. For us, the things that we're mostly going to focus on are things that are maybe slightly technically called boosts. And these correspond to transformations between two reference frames that are moving at a non-zero relative velocity with respect to each other. But from the point of view of just general information about what I'm going to talk about in the second half of class, the things that I'm not going to test you on, it's actually quite useful to look in more simple transformations of simply translational changes between two reference frames and rotational changes or rotationally varied coordinate systems. So I'm just going to take a little bit of a deviation on that now, just again, it's more or less FYI. Most of what I'm going to talk about today, except for the Lorentz transformations and length contraction, are FYI, okay? So I want this to be a somewhat leisurely session this morning. Okay, so translations, what does it mean? I'm simply taking two coordinate systems, two observers, two reference frames, and as you're getting used to now, you're starting to see things so-called non-primed and primed. And so the typical thing we might consider in this case is a Cartesian coordinate system for the non-primed observer O, X, Y, and Z in this orientation. And this is some event that's taking place at a certain location and a certain time. You saw that in my initial slide cartoon on Tuesday. And then a second observer, second reference frame, the prime reference frame, and in this case it's just a translation. So it's simply a fixed displacement, okay? So everything's primed in this reference frame. They're not moving with respect to each other, they're just translated, okay? So if we were to look at sort of transformations of coordinates, if you will, and just say how do the coordinates transform, well, here I'm keeping spatial and temporal coordinates separate, and what you would imagine in a case like this is just there's a fixed offset, both in space and time, in terms of how I would measure where, or when and where that event took place, okay? So I assume it's pretty clear that we would have a simple spatial offset in the spatial coordinates. Temporal offset just comes because presumably we're a certain or different distance away from the event. And so measuring when it took place is presumably going to give us an offset as well. So not very interesting, sort of more or less what you would expect. What about if I rotate two coordinate systems now? So they are not translated, so in that sense they have a common origin. O and O prime are together. This sketch didn't particularly come out, well, it's the sort of most generic rotation that you could imagine. So I'm rotating this about some angle that in this little sketch here doesn't appear to be in any of the planes defined by the three coordinate axes. So it's some arbitrary rotation about this origin. So, how could I describe the translation between these? I'm wondering why I've lost my red dot here. Let me just see if I can get it back. It's not there. The way I can figure out a transformation for an event, imagine my red dots up here. Well, in terms of spatial coordinates, if you think about this, I can describe it in terms of a general matrix, and I'll show you an example of this on the next slide. Simply a rotation matrix that relates the coordinates in the primed and non-primed frames, okay? The time, since the origins are the same, and I've got my single event up here, presume the time measured in both of these reference frames is the same, okay? So let me look at this in a slightly more specific example. So here it is. Now I'm taking a rotation, again, fixed origin for both of these. And now I am actually rotating it explicitly in the XY plane to keep it slightly simpler. And I'm doing a rotation of the primed reference frame by an angle phi with respect to the, let's say, original non-primed reference frame. Okay, so pretty straightforward. Here's the idea then of a rotation matrix, and you can figure this out very easily just by doing some simple trigonometry. Of course, the z coordinates don't change. There's no rotation in that direction. But in the xy direction, I need simply to fold in some trigonometric quantities that give me the relation between non-prime and prime. So again, you can easily do this, and then I can put it in matrix form. This is a nice way of representing a rotational coordinate transformation with a rotation matrix. Okay? So, fairly straightforward. And the reason I introduce this is we're going to come back and use something similar to this when we talk about some of the sort of FYI topics later on. All right, so just setting the scene. Now let's actually turn our attention to the thing that's most of interest to us in the sort of problems we're going to have to deal with. And these are the so-called boosts, okay? So this is the case where there is a relative velocity between the two reference frames. So here's O, and here's O prime. And it's moving with some relative velocity v. Okay? Now we might happen to choose, just for convenience, that at time t equals 0, these two reference frames overlap. Okay? Well, the two origins, I should say, overlap. Okay, so these are more complicated, and it's in this context where the speed of light becomes important. And so I'm basically just going to kind of show you what these transformations look like. And so here it is. So here are the transformations that we need. I'm not particularly worried about deriving them. It's not too difficult to do so, and I think our textbook goes through it. But with the usual definitions now, we've got a, let's say, non-moving reference frame O and a moving reference frame O prime. In Galilean world, we would have this type of transformation. And in this case, we've got the velocity specifically oriented along the direction of the x-axis. Of course, that's a choice that we made. But in Galilean world, we would simply offset the x-coordinate position by an amount that looks like this. And I think if you look back to early in the semester, you'll have done a little bit of exercises on simple transformations of this type, when we looked at relative velocities, for example. And of course, what you see here is that time is kind of universal in the Galilean worldview, so there's no explicit transformation of time in this picture. So, when we move over to special relativity, and again, keep in mind this is for relative motion along the x direction, then in some sense this looks somewhat familiar, but of course it's now got this gamma factor boost in there. And so our transformation of the coordinate measured in the moving reference frame, we're going to write as gamma times x minus dt. Okay? And associated with this is a transformation in the observed time between these two coordinate systems. And again, it's starting to get a little bit more complicated. We're not going to derive this, we don't need to, but again, if you want, take a look in the textbook or maybe one of the supplemental resources that I've pointed you to. So here's the key difference. So these are the Lorentz transformations, and in a sense, this is kind of the only thing that I'm really possibly going to test you on in the course. The phenomenon that we've seen already of time dilation and the one that we're about to see in terms of length contraction are simply examples of applying these Lorentz transformations. So if you can start to build up a certain level of comfort with this, and I know it's confusing, the link that Luis sent me, which I forwarded to you overnight, I thought was nice in the way that it started out because it just talked a lot about the confusion associated with all this and how hard it is to keep track of which reference frames you're measuring things in and so on and so forth. So I know it's hard, but the reality is if you can basically build up some comfort level, I won't say intuition yet because it's really never going to be intuitive, but some comfort level with using these, you're going to be in good shape, at least for what we need for this course. Yeah?
Is this only assuming like motion horizontally? That's why I don't really...
Well, explicitly it's assuming motion along the direction of the x-axis. So if the x is horizontal, sure, yes, it means only that. Yeah.
How does that vary when you have motion along both lines?
So as you might imagine, you're going to have to worry about components. But really it's just a question of setting up your coordinates in a way that you can easily apply these transformations. So whenever you've got a velocity component along one of these directions, you're going to have to fold in that velocity component in the same way that you've done here. Okay? But usually all you need to do is rotate your coordinate system so that you've got it pointing along the direction of relative velocity, right? That's obviously the easier way to do it. Okay? So I know, and again, the challenge comes in actually applying this in problems. What I have not quite figured out how I want to do yet, I will figure it out by tomorrow, is I want to make sure I've given you a few work problems to go through. I'll post those on Courseworks. But I also, next week, with the recitations with Ben and Reese, want to make sure that they're also ready to cover a couple of sort of sample problems on using the Lorentz transformation, so that you are getting good practice with this. So then, again, this is kind of what you're aiming for understanding of this small section on special relativity. We're going to kind of turn around and go back again to a certain special kind of phenomenon associated with this, related in some respect, so the inverse behavior, to the time dilation phenomenon we talked about on Tuesday. So the sort of other phenomenon that's often introduced as an immediate corollary of the transformations is this thing called length contraction. And it's equally perplexing. And briefly, what it's saying is that the spatial extent of an object in the direction of relative motion between two different observers the spatial extent along the direction of that relative motion, or the length, if you will, depends on which reference frame you're in and depends on the relative speed with which those reference frames are moving with respect to each other. Okay? So, what you can do, for example, is imagine something, some rod, some meter stick, and you're basically measuring this, in this case where I set up the origins to coincide at time t equals 0, you're measuring the length of that object at that time in both reference frames. And if you simply go ahead and take that x coordinate transformation